Okay, so this video we are going to finally look at starting to calculate some enthalpy values, okay? So last video I kind of ended talking a little bit about combustion. So you're going to find we are often going to talk about molar enthalpy of combustion. So remember we talked about molar enthalpy in a previous lesson. We said that that was measured in terms of kilojoules per mole, okay? So you're going to find that as we go through this unit, we always use delta H, but you'll notice there's this little C here. Okay, we kind of have a couple of different symbols we use. We tend to use C because C stands for combustion. That's not how you spell combustion. That's also not how you spell combustion. We also use F for formation, and then we use R. Okay, R is basically for everything else. So anything that isn't combustion or anything that isn't formation, it just means reaction, okay? But yeah, you're going to notice that we often will put a little symbol there, and it's just to kind of specify what type of reaction it was. So was it a combustion, was it a formation, or was it some other type of reaction? So when we are specifically talking about molar enthalpy of combustion, we are talking about if you burned 1 mole of whatever that hydrocarbon is, how much energy would be involved in that, okay? So when we are talking about combustion, there is 2 different sets of conditions, okay? There is that open system, or there is more of that closed or isolated system, okay? The biggest difference is going to be the states of water. So what you're going to find is that in an open system, because the reaction occurs at constant pressure, right, as we produce gases, they're able to leave and escape, the water gets to get that L subscript, or sorry, not an L subscript, what am I saying? It gets a gas subscript, right? That's usually what we have with our combustion reactions. But what you find is that in those closed systems, the water is going to be a liquid, and that's because the high pressure forces it to basically liquefy. So open system, it gets to be a gas. A closed system, it's going to be a liquid. Okay, and things you should recognize as being closed system, cell resp is going to be one of those. Photosynthesis is going to be another. Bomb calorimeters, when we start talking about those. Those are kind of the 3 major scenarios where the water is going to be a liquid. Okay, every other time you get to do water as a gas, it does exactly what you expect it to do. But it is important for you to recognize the difference, because what you find is that the enthalpy change is different depending on the state of water. So if you put the water as one state when it was really supposed to be the other, you're going to come up with a different delta H value, because when you look in your data booklet, you'll see that water is in there twice, once as a liquid and once as a gas. So really important to make sure that you are capable of distinguishing, should it be a gas because it's an open system, or should it be a liquid because it's a closed system? So either it's a bomb calorimeter, photosynthesis, or cell resp. Okay, so now we're going to start talking about calculating those enthalpy changes. So last video, we looked at thermochemical equations, right? We looked at 3 different ways to write it. We also talked about how those thermochemical equations were 4R equations the way they were written. So that means I basically can create a ratio using the kilojoules and whatever number of moles I balance my equation with for whatever chemical I am given information for. Okay, so here's an example of a question like that. So it says, what is the enthalpy change when 50 grams of methane undergoes complete combustion in an open system according to the following equation? So here's my thermochemical equation. Here's my delta H over on the side. So what we have been given in the question is the mass of methane, right? We have been told 50 grams of methane. Okay, same deal as always. When I have a mass, I'm going to need to go get a molar mass. So methane is going to be 16.05 grams per mole. Okay, so from here, what we can do is basically a unit analysis calculation, okay? So think about the units you're trying to solve for, right? We are being asked, what is the enthalpy change? So that means we are trying to determine kilojoules. So because we are calculating the enthalpy change, that means that we are looking to calculate delta H, okay? So we need kilojoules. The only thing that has kilojoules right now is this delta H right here. So that delta H is negative 802.5 kilojoules. What's going to go on the bottom of this ratio is going to be 1 mole of methane, because that's how much I have in my balanced equation. So 1 mole CH4. Okay, so we're almost always, when we have this thermochemical equation, going to be generating a ratio using that delta H, either if it's tabbed off on the side or within our equation, with however many moles we balanced with of the chemical we have info for. So from here, we can cancel the moles of methane by using the molar mass. We can go moles CH4, and that can go over that 16.05 grams, right? And from this, we can eliminate the moles of CH4. Okay, then the next unit we need to get rid of is grams. We can get rid of that using the 50 grams. So we can just go times 50.00 grams. And then from here, those grams are now gone, and we have solved for kilojoules, okay? So go to our calculator. We're going to do negative 802.5 divided by 16.05 times 50. And that's going to give us negative 2,500 kilojoules. And we are allowed to have that many significant digits, so we don't really have to do anything to it. If you want to switch it over to scientific notation, you could, but it's not a crazy huge number, so it wouldn't really be expected that you would do that, okay? So pretty common type of question. You have to be able to recognize that you can calculate delta H from a thermochemical equation by generating a ratio using that enthalpy change along with whichever chemical in your equation they have given you information for, okay? You also can kind of work backwards. So the next question is still linked to that one. So determine what mass of oxygen is consumed during the combustion of methane given an enthalpy change of negative 250 kilojoules. So if we're looking for mass, we're obviously going to need the molar mass. So for oxygen, the molar mass is 32 grams per mole. Okay, so I should really have just kind of copy pasted this over. Well, can I? Let's see if it'll let me. Take that, we'll steal that over to this slide. It's missing the arrow, but that's not really a huge deal. Can throw one in. Okay, so here's our equation. We have that associated with oxygen, right? Because we are trying to find the mass, and we have been told that 250 kilojoules were released, right? So we know that for whatever unknown mass, right, we release negative 250 kilojoules. So again, I'm doing unit analysis, so I'm thinking mass of oxygen, I'm trying to find grams. So I'm going to start with the molar mass because that has grams. I'll put that as grams per mole of that oxygen. Okay, so to get rid of moles of oxygen, we're going to use our ratio. So we are going to do times 2 moles of oxygen, right? Because that's what we have in our balanced chemical equation up here. There's a 2, and that's going to go with that negative 802.5 kilojoules, right? Because we said that in this unit, our ratios are generally going to involve the delta H value of the enthalpy change along with the other one. So from here, moles of oxygen is gone. Last unit I need to get rid of is the kilojoules, and look at that, we were given kilojoules. So we can then times by negative 250 kilojoules. And that's going to allow for us to cancel out kilojoules, leaving us just with grams. So 32 times 2 divided by negative 802.5 times negative 250, we get a mass of 19.9 grams, okay? So different types of things that you can calculate from that thermochemical equation depending upon what information the question has given you. So most of the time when you see you've been provided with the thermochemical equation, you are probably going to be doing a unit analysis style question where you are using that enthalpy change in the form of a ratio somewhere within your calculation, okay? So now we're going to start talking about calorimetry, because calorimetry is the method that we use when we are trying to experimentally determine how much energy a chemical reaction gives off. So a calorimeter is basically a device that we can use to measure changes in thermal energy. There's different types of calorimeters. Today we're going to talk about a simple calorimeter. In another video we're going to talk about flame calorimeters and bomb calorimeters. We use them to measure different things, okay? But they all work off the same principle, okay? So when we are dealing with calorimeters, we tend to make the assumption that they are isolated systems, okay? And what that means is the amount of energy that goes into my system at the very beginning before I close it all up is the same amount that we have later. And the reason that we tend to have to make this assumption and not have too much choice in the matter is because we want to be able to relate these things. We want to be able to say that Q1 is equal to the negative Q2, right? Remember we talked about this in the first intro to thermal lesson. We were like, well, if something absorbs energy, something else has to release it. That's kind of the main premise behind a calorimeter, is that my chemical reaction, which generally is what we call a system, okay, you got to find we use the word system and surroundings. And most of the time when you guys think endothermic or exothermic, you think of like the air as being the surroundings, okay? In this case of a calorimeter, we usually tend to use water. Okay, the reason we tend to use water is we can contain water within our calorimeter really well, right? It pours easily, it's easy to measure, it's a safe chemical, that type of thing. And so the water is almost always going to be what we call our surroundings. And the system is our chemical reaction that is happening in it. And so what we generally wind up finding is that whatever happens to the water happens because of what happens in the system. So this is where sometimes you guys struggle, because usually when we first start talking about thermo, we talk about like, ooh, the energy moves from the hot object to the cold object. And that is true when I put two objects together that start at different temperatures. But when we're talking about chemical reactions, it's not that the temperature of the chemicals are changing. It's actually that we're looking at that bond breaking and bond forming, right? So remember in the previous video, we talked about how energy has to be input to break bonds, and then energy is released as those new bonds formed. And we said what determined overall whether a reaction was endothermic or exothermic was which of those steps had the bigger energy requirement. So when we talk about using a calorimeter and a process being endothermic or exothermic, usually you guys are like, yeah, okay, the water got hotter. I get that. But then you guys want to be like, well, but that means my chemicals got colder. And that's not the case. It's not that the chemicals got colder. It's that I put a certain amount of energy in to break the bonds, and a certain amount of energy was released as I formed new ones. So if overall forming the bonds released more energy, then I'm going to see that the temperature of the water is going to increase, okay? And that's because the potential energy, which was stored in the chemical bonds, was converted into thermal energy, okay? So generally when we are talking calorimetry processes, one of two things happens, okay? Either potential energy gets converted into thermal energy, or thermal energy gets converted into potential energy. Okay, so if it's potential energy converting into thermal energy, that means that that was an exothermic process. And I released energy overall because it was less energy stored in the bonds of the products than that were stored in the bonds of the reactants. If I find the opposite, though, and I find that thermal energy was converted into potential energy, I'm going to find that the water got colder because we pulled thermal energy from the water to use it to create potential energy because we needed more energy to break the bonds than was released as we formed them. Apparently I am randomly zooming in on pictures, okay? So important to recognize that the temperature changes that we see happening in the water do not correspond to an opposite temperature change for our chemicals. It corresponds either to thermal to potential or potential into thermal, okay? So an endothermic process is going to reduce the temperature of the water in the calorimeter because that energy is being absorbed into the reaction. Okay, an exothermic process is going to increase the temperature of the water in the calorimeter because overall there's an excess of energy, so that potential energy gets converted into thermal energy, raising the temperature of the water in the calorimeter. So normally we'd be heading to the lab and we'd be doing some experiments using some simple calorimeters. So simple calorimeters are basically styrofoam cups with styrofoam lids. And that's because for the most part, styrofoam's a pretty good insulator, right? You think about if you have a hot drink, you can put it in styrofoam, it'll stay hot for a while, right? Not going to stay hot indefinitely, but think about how quickly we tend to do chemical reactions. We're done them in, I don't know, 10 minutes at most. So using a styrofoam cup, we're not going to lose that much energy or potentially gain that much either. So generally what we have is we double up the styrofoam cups on the bottom just to give us that extra insulation. Okay, we then fill the styrofoam up with water, and that's because water is really easy to measure the temperature of. It's easy to weigh. It also has a really high specific heat capacity, right? It's 4.19, and a lot of other things are around 1. So that means it takes quite a bit of energy to change the temperature of water, which is why sometimes you'll see that, like, if your car starts overheating because you don't have any more of the fluid, you can pour water inside and it's good enough to get you to a station where you can definitely get some new fluid, coolant fluid to put into your engine, okay? So doubled up styrofoam cup, water. Our chemical reaction is going to happen in the water. So obviously, I cannot use a simple calorimeter for a combustion reaction because combustion doesn't happen in water. But I can use it for other type of chemical reactions that are not combustion equations. Okay, there's then a lid that goes on top. This diagram shows you a stirrer and it shows you a thermometer. We generally tend to just use the thermometer and we stir with the thermometer, so we don't actually need a stirrer as well. If anything, that just introduces an additional hole, which is another spot for energy to escape. And we really want to try to minimize how much energy escapes because we want to be able to assume that the amount of energy inside is constant and that it is that isolated system, okay? So if we were in the lab, and you're going to hear me say that a lot in this unit because this is actually a unit where we would probably spend almost just as much time in the lab as we would in the classroom. You would see that for the most part, your percent errors are pretty atrocious in thermo. And that's because we're forced to make a lot of assumptions that aren't always true, right? We're forced to make the assumption that these are isolated systems. And so it's just Q of the water is equal to negative Q of the chemical reaction. But that's not really true, right? We are going to lose some energy. We are potentially going to gain energy, especially if you're like, let's say your hands are really warm and you're holding the outside of the cup and you're stirring really vigorously. That's not going to be a valid assumption, but it's an assumption we make nonetheless. Just like we make the assumption that even though this is water, that we've probably put some chemicals into it, we still make the assumption that it has the same specific heat capacity as water, which really it's going to be super close, but it might be a hint off. So lots of room for error inside of this. So Really the only thing that should be able to escape from a simple calorimeter is going to be if you produce a gas, because those are going to be able to sneak out through the hole where you have your thermometer in. Because although in this picture it looks like it's a really snug fit, it's never a snug fit, right? The more you stir, the bigger you make that opening. So definitely there's more opportunity for stuff to escape. So steps to use a simple calorimeter. First thing we'd want to do is actually determine the weight of the calorimeter, because once we put water in it, we wouldn't really know how much of the mass is due to the calorimeter versus how much is due to the water. But you could just put the calorimeter on, zero it, and then place your water, okay? We always need to know the mass of water because we need the mass to be able to do the MC delta T, okay? We then need the initial temperature of the water so that we know what the initial temperature is. You would then add the reactants to the calorimeter. You would, as quickly as you can, stick the lid on, stick the thermometer in, and start to stir it. You then are going to stir it until you either reach the highest temperature or the lowest temperature. So you're going to notice temperature is either going to climb, and then it's going to stop, or it's going to drop and drop and drop, and then it's going to stop. So at whichever point it stops, that is where you're going to record the final temperature. Okay, so we need to know the mass of water. We already know what C is for water, so we don't have to worry about getting that from our experiment. But we have to be able to get the delta T, which we get by knowing the initial and the final temperature. From there, we can calculate Q because we have the M, we have the C, and we have the delta T. Okay, so discussing really quickly why calorimetry works. So it's basically all based off of those laws of thermodynamics, right? Law number one, energy is conserved. So whatever energy was inside of that calorimeter when it started is the amount of energy that's still in it at the end. So when we see that the surroundings or the water gained energy, it must be because our chemical reaction released or lost energy. If we see the opposite, then it's the opposite. I'm having issues here. That is the opposite thing that happened, right? If we see that the water got colder, then that energy had to go somewhere and it must have gone into our chemical reaction. And now it's being stored as potential energy inside of our products, okay? Okay, so the surroundings is the water, the system is the chemical reaction. So we're always able to measure the MC delta T of the water. We then can use that to determine what the enthalpy change was for our chemical reaction, because we know that the numerical quantity should be the same. The only difference is going to be the sign, right? So somewhat similar to those calculations we did on the first day, we can relate those two things. The difference becomes what those two things are that we are relating. We're now saying, instead of Q1 equals Q2, we are saying that delta H of our chemical reaction is equal to the negative Q of the surroundings, which is pretty much always going to be the water when we are looking at those calorimeters, right? So we have that delta H equals negative Q of the water. Well, how do we calculate Q of the water? We calculate it by doing MC delta T of the water. So we can basically generate the equation that delta H equals negative MC delta T. And that's the equation we're going to use when we use simple calorimeters. When we use other types of calorimeters, you're going to find that it's going to change because we're going to have more things absorbing energy. Okay? When we deal with the simple calorimeter, we basically assume that that styrofoam cup does not absorb or release energy, and we just omit it. We pretend it's not even there. We pretend that the only thing that matters is the water. Okay? So this basically goes on to describe all of that for you, so you can see that down here. If you want to read a little more, you have that in your copy of the notes. So using a calorimeter. Kind of also already talked about all of these different steps. Again, it's challenging in that we can't actually go to the lab and do some of these experiments, but it's still really important that you are able to do these calculations. So We're going to have a look at a couple examples of what this is going to look like. So the one thing you have to make sure that you are reading carefully when it's asking you to calculate enthalpy is it just asking for enthalpy or is it asking for molar enthalpy? Because if it's just asking for enthalpy, then I'm basically just calculating Q because I'm just looking for kilojoules. But if it's asking for molar enthalpy, I have to calculate kilojoules per mole. So I'll have to not only do MC delta T, but I'll also have to know how many moles of whichever chemical was involved in the reaction that I used. Okay, so we have an example here. So octane is one component of gasoline. The heat produced by burning 1 gram of octane is collected in 2.95 kilograms of water in a calorimeter. If the temperature rises by 16.25 degrees C, calculate the molar heat of combustion of octane. So this has asked molar heat. So that means unit-wise, I need to be getting kilojoules per mole, and specifically moles of octane. Okay, so if we look at the givens we have, right, whenever we're doing calorimetry, we should have MC delta T for water. So we have the mass of water is 2.95 kilograms. Okay, and you're going to find that I want kilograms because I'm trying to get kilojoules. And remember we talked previously about how we have to make sure that if we're doing kilojoules, we're in kilograms. If we are looking for joules, then we could use grams. So there's our mass. Our specific heat is going to be 4.19 kilojoules per kilogram degree C. Right, so again, we talked about this before, same C value, but we've changed those units. And then we were given that delta T, which is going to be positive 16.25 degrees C, right? Because it said the temperature rises, which is why it's positive. So there's my MC and delta T. So that's how I'm going to get the kilojoules part. I need to get the moles part as well. So to get moles of octane, I have a mass of octane, right? I know that the mass of the octane is 1 gram. So that's going to mean that I also need to go get the molar mass of octane. So octane is C8H18. So getting the molar mass for that is 114.26 grams per mole. Okay, and if you were like, how was I supposed to know that was the formula for octane? Remember in your data booklet, you have that table that shows you all those common formulas and names. Octane is most definitely in there, okay? All right, so how this calculation is going to work. So I'm just going to copy that symbol so I don't have to keep going the long way. We are trying to calculate molar enthalpy. So symbol for molar enthalpy, sorry, hold on a sec here. Delta pasted itself up there. Okay, so symbol for that, delta H. Unit-wise, I am looking to get kilojoules per mole, okay? So we are going to calculate this using the negative MC delta T of the water. And that's because, remember we talked about how it's Q1 equals negative Q2? We need to make sure we put that negative in because the water is doing the opposite. So as a general rule, any calorimetry question, you should be starting your calculation with a negative. Okay, and that's because we're using the water to determine the enthalpy change of something else. And the water is going to do the opposite, right? Because the water is the surroundings, the delta H is for our system. They are opposites with respect to what happens to that thermal energy change. So it's going to be negative. And then I'm going to use that MC delta T. So I'm going to do the 2.95 kilograms times about 4.19 kilojoules per kilogram degrees C. All right, and that lets me cancel out my kilograms. Getting rid of the degrees C, we're going to use that 16.25. So times 16.25 degrees C, right? So there's my M, there's my C, there's my delta T. When I look at my units, that gets me the kilojoule part. Now I need to get the per mole part. So this is where I'm going to use the molar mass. And I'm going to say times 114.26 grams per mole, so that I am placing the moles on the bottom, which is ultimately where they need to be. Then we need to get rid of the grams, right? Because we just want kilojoules per mole. So to get rid of grams, I'm going to use that 1 gram over here. And we're going to put it on the bottom. So we're going to say times 1 over 1 gram. And then from here, we can cancel out grams, and we are left with the kilojoules per mole. Okay, so negative 2.95 times 4.19 times 16.25 times 114.26, and then divided by 1, we get a really big number. So we get negative. I am going to switch over to scientific notation. So 2.30 times 10 to the 1, 2, 3, 4 kilojoules per, having issues, kilojoules, oh my goodness, kilojoules per mole, okay? So this is kind of the general layout that most of your simple calorimeter questions are going to have. They're going to have negative, and then they're going to have that MC delta T of the water part. Then they're going to have you determining how many moles you have of whichever reactant they gave you information for, okay? So again, like I mentioned previously, the challenging part as we go further in this unit is you're going to see there's a whole bunch of different ways that you can calculate delta H. And the issue tends to be when we get to the end of the unit is you guys are like, well, am I doing this or am I doing one of the other 5 other ways that you showed me? And the hard part is there isn't really a specific thing to tell you. You really have to look at what you were given, right? So in this case, I was given calorimetry data. So if I'm given calorimetry data, I should be doing a calorimetry style calculation, at which point I'm deciding what type of calorimeter is it. So what type of calorimetry calculation is it going to be? Generally, we assume it is a simple calorimeter and it's this type of calculation, unless the question gives us information that tells us that it is not a simple calorimeter. Okay, if I don't get any calorimetry data, then obviously I can't do a calorimetry calculation because I don't have the ability to determine the MC delta T of the water. Okay, so those are things to be thinking about as you practice answering questions. So here's one that looks quite different, but you're going to see that it's actually not really that different. So it says if 50 mils of 0.3 molar copper sulfate is mixed with 50 mils containing an excess of sodium hydroxide. The initial temperature of both solutions is 21.4 and the final temperature is 24.6. Determine the enthalpy change for the reaction and write a thermochemical equation. So eventually we have to write that thermochemical equation. So we know that we are combining copper sulfate with sodium hydroxide. Okay, this is going to give us copper hydroxide, which if you check your solubility table is a solid, along with sodium sulfate, which again, if you check that solubility table, this one is going to be aqueous. So to eventually turn this into a thermochemical equation, I have to be able to calculate what is the delta H for this reaction, okay? So I'm going to figure that out using the information that was given to me in the question, right? So we were told that we had 50 mils of the copper sulfate and that it was at a 0.3 mole per liter concentration. We were told for the sodium hydroxide that we also had 50 mils. We were not given a concentration for this one. Instead, we were just told it was in excess, okay? So when you think about it, when I look at these reactants, the one I'm going to be able to determine moles for is going to be the copper sulfate, because I can convert milliliters to liters. That'll allow for me to get rid of the liters and give me moles, okay? So that's going to be the one that I am going to be finding. So we need to calculate our delta H. So this is going to equal negative, because we are using the water. So some of you might be saying, well, wait a second, we don't have water. But remember we talked previously about how we can assume that solutions are water? So if I took 50 mils of copper sulfate and I mix that with 50 mils of sodium hydroxide, right? So I had my little container, and then I went and into that, I put in 50 mils of the copper sulfate, and then I put in the additional 50 mils. Right now, inside of here, this all gets mixed together. I now have 100 mils. So from that, if I have 100 mils, I have 100 grams of water. But we've talked before about how delta H should be measured in kilojoules. So I don't want 100 grams, I want to convert that over. So we're going to use 0.100 kilograms. So there's our M, right? Now we need to do our C. So we're going to use that 4.19 kilojoule per kilogram degrees C. Then I need my delta T. So the question said the initial temperature is 21.4 and the final temperature is 24.6. So if I want to calculate my delta T, right, it's going to be 24.60 minus 21.40. So 24.6 minus 21.4, I come up with 3.20 degrees C. Right? And two numbers after the decimal, because this had 2 and this had 2. So this is going to be the number that I'm using in my calculation. So here, we're going to say times that 3.20 degrees C, right? So again, looking at the units, kilograms are gone, degrees C are gone. I have now calculated kilojoules, but I need it per mole, and this is the one that I had moles for. So moles has to go on the bottom because it has to be kilojoules per mole. So I am going to flip that over. So liters on top, on the bottom, 0.3 moles. And that is going to be of that copper sulfate. I need to get rid of liters. I had 50 mils, so to get rid of liters, I need to put that on the bottom. So 1 over 0.0500 liters. Okay, and now that lets me cancel out these liters. Okay, now I'm left with kilojoules per mole. So negative 0.1 times 4.19 times 3.2 divided by 0.3 and divided by 0.05 is going to give me negative 89.4 kilojoules per mole. Okay, so now we want to turn this into a thermochemical equation. I have two ways in which I could choose to do that. I could choose to write this as a delta H tabbed off on the side, at which point I'd literally just write that delta H equals negative 89.4 kilojoules, or I could choose to write it within my equation. Whether it goes on the reactant side or the product side is dependent on the sign. So because this is negative, that means that this would go over here on the product side, right? So I would be writing plus 89.4 kilojoule. Okay, you'll notice that I got rid of the per mole. And the reason I got rid of the per mole is this is for my equation as it's written. And when you look at it, I already have 1 mole of copper sulfate. So that's why I can just put it in as 89.4. So let's say, though, that there was a 2 in front of this. Then because this would have been per 1 mole, I would have had to double this value before I wrote it. And if it was balanced with a 3, I would have had to triple this number before I wrote it. But in this case, because I have 1 mole in the equation and I just solved for 1 mole, that's why I can put the number as it is directly into that equation, okay? So There are quite a few questions in here from old diplomas for you guys to give a try on. Some of them are multiple choice, some of them are numeric responses, but you'll see they're all basically looking at the same thing, right? Look at the two calculations we just did. We did negative MC delta T of the water, and then we figured out how many moles we had, and we basically divided by that. And here we did the same thing. We did negative MC delta T, and here we figured out moles. The only difference was here we got moles from a solution, and the last question we got moles from mass and molar mass, okay? So these are your simple calorimeters and what your calculations are going to look like for simple calorimetry calculations.